All right, I don't have, if you notice, I don't have the assignments in yet because I'm going to redo those as well. So they won't be showing up until Wednesday, most likely. So we're just going to do notes today, and then we'll have the assignments by Wednesday. So try to get this PDF open. It might work, it might not. The way things are going this morning, and it's just sitting there spinning. So, huzzah, it opened. I think they said that a lot of it has to do with traffic, because Monday, it's the Moodle servers haven't been used pretty much all weekend, and then everybody's trying to get on them on Monday morning at different locations, be it here or over at the early college building. I did fix the, I don't know if you call it a typo if it's handwritten, but whatever I did to mess that up, I fixed that. And I uploaded the same page twice. Okay, so so this is the fixed one. So I forgot to take this one out of the stack. Of course I did. And I uploaded it to every single class I had, so I get to do it again. I'm so happy. For God's sake. All right, here we go. All right, we're going to start with probability. Okay, so a couple of things to know beforehand about probability. I kind of mentioned this last week. If I didn't, I just forgot. But I am not very good at probability. Never have been. I've always struggled with it. I think when they were first going over it when I was in school, that I was sick. So I tried to simplify it as best as I could. Now, that being said, if you had 143 previously, I know there was a lot more of it covered than what I'm going to do today. Mainly just because what I did cover, I went into a lot of detail on. So there's that. But also because probability is very confusing. Okay? Maybe not for you, but it is for me, so I'm going to take my time. All right, just to be on the safe side. So the 4 aspects of probability that I've got up here, I'll go ahead and let you know, because I'm going to put it on the whiteboard here in just a second. All of these came out of 7A in the textbook. If you want to go ahead and flip over there. So, probability, and it all came from 7A. Okay? So, let's stay in the PDF notes for now, then we'll hop to the whiteboard here in just a second. All right, so 4 things about the 4 types of probability we're going to talk about, mainly because they all sort of work together. We've got theoretical probability, relative frequency probability, subjective probability, and then we talk about events not occurring and what odds are and how they work. Now, not really like betting odds, because those work pretty much in a different way. So I figured I'll just leave that out. Okay, and do that every single class. Okay, so let's hop over to page 413, and let's talk about theoretical probability. Okay, so a couple of things about theoretical probability. It's based on the assumption that all outcomes are equally likely. So it mainly deals with things like, rolling a die, or, a deck of cards, things where every outcome has an equal chance of happening. The way it's found is it's determined by dividing the number of ways an event can occur by the total number of possible outcomes. So there's the formula there. Now, in the book, on page 413, let me catch up to y'all. All right, 411, 413. All right, so in the book on 413, every time, this time and every time forward, whenever we see a probability formula, it's going to say P of A, or P on the outside of A in parentheses. What that means is the probability of event A. And all event A is what you're investigating, what you're looking at that might happen. Okay? So another way to think of theoretical probability is thinking of it like what should happen. All right? So if we look at it like that, let's look at 25 on page 422. All right, I'm going to be hopping back and forth a lot within 7A because most of the problems that I want to look at are at the end of the page, or end of the section. Lord, I'm all over the place today. All right, which one did I say? 25. Okay, thanks. I'm going to kind of use y'all as my backup memory today. Okay, so on 25, it says, the question says, for 19 through 28, use the theoretical method to determine the probability of the following outcomes and events. State any assumptions that you make. So 25 wants to know, what is the theoretical probability of a randomly selected person having a birthday in January? Okay. Now, like I've said before, I've been totally honest with you guys. I'm not good at probability. First time I did this one last night, I got it wrong. I wasn't lying. I really have to work with probability. The first time I did it, I was thinking, look, okay, there's 31 days in January, so a randomly selected person having a birthday in January, that's 1 out of 31, right? No, it's not. Yeah, that's not, yeah, I did it completely wrong. All right, so rewrite the formula for theoretical probability. Okay, so theoretical probability. All right. Okay, oops, not. Okay, so the formula for that is the probability of event A is equal to the number of ways A can occur. There's no E on the end of occur. Over the total number of possible outcomes. Okay. One thing that I've found that kind of helps me get these straightened out is to do the total number of outcomes first. All right. So what's the total number of possible outcomes as far as different days out of the year that someone could have a birthday? Right. There's 365 days in a year. So, well, we're not, this is bad enough as it is. So, yeah, there are 365 different total days that any single person could have a birthday out of the year, right? Okay. Now, if you're just looking at a birthday in January, that is your A. Okay? The birthday in January, that's your A. Well, how many days are there in January? 31. All right? So 31 out of 365. Now, depending on how the question is set up, excuse me, sometimes they're just not going to outright say, you know, leave it as a fraction, leave it as a decimal, leave it as a percent. But most people associate probabilities with percentages. So just, you know, make it a percent real quick. So you divide 31 by 365. That gives you 0.08, which will give you 8%. So for now, we'll just, you know, we'll count them all. Now, whenever I do make your assignment, there will be clear choices for you to pick from, because I don't want to leave any kind of... Yes, Ever? Well, you're not far off, but what you're thinking of is the next kind of probability we're going to look at. So that's a good question. Yeah. Yeah. What this says, to kind of piggyback off what Ever said, because did everybody hear what she said? Ever said it kind of feels like there should be a number of people that we're looking at. That is relative frequency probability that we're going to look at here in just a second. But remember, theoretical probability is what should happen. All right? So it kind of goes along the lines of, like, let's say if you have one die, like a 6-sided die, and you want to know the theoretical probability of getting a 4. Well, what should that be? 1 out of 6. If you have a coin and you want to know the theoretical probability of it landing on tails, what's the theoretical probability for that? 50%. Theoretical probability, you don't have to have a observed number of outcomes. Theoretical probability is, you know, you're looking at your whatever you're trying to do and you say, okay, this is what the probability should be. All right, so in this instance, if you're just looking at any randomly selected person that had a birthday in January, how many different ways can that occur? Well, that is 31 out of 365. So there's an 8% probability that if out of any randomly selected person that their birthday is in January, out of all the months, out of all the days. Only 8%. All right? So that is what makes theoretical different, is because you're not actually observing anything, you're not recording any outcomes, you're not actually doing the experiment or whatever it is. You're just looking at the situation that was presented to you and you're saying, okay, this is what it should be. That's why it's called theoretical. Yeah. One out of 12? Is that 0.08 or 8%? Okay. Well, this is how they had it down in my materials. So that's just the way I did it. Yeah. Yep. Mainly, too, though, I think they did it this way because not all the months have the same amount of days in them. But there are, for sure, except for the leap year, 365 days out of the year. So that's why they went with that one, because it's a little bit more concrete that way. All right. I'm sure you're going to have more questions about theoretical probability later, because like I said, it's probability and it stinks, but that's just kind of how it is. But for now, anybody unsure as to how we arrived at 31 out of 365 for this? I kind of went through it quickly just because I've got a pretty good amount of notes to get through and got a late start. So is everybody good on this one for now? We can come back to it later if you need to. Just make sure you got it jotted down, or just, you know, make a note on where we were at in the PDF. Okay? So this one was theoretical probability. All right. So let's go back to the PDF. Let's look at the one that Ever was asking about, relative frequency probability. Ooh. Okay. So that's on page 416. Relative frequency probability is. So Lots of hopping. Okay. So, like I said, we're looking at 3 different ways that you can figure out probability. So the second way is relative frequency. This one is based on actual recorded observations, okay? It's based on observations or experiments. Where it comes from is the relative frequency of the event or interest. So kind of piggybacking off of what Ever said. Let's say maybe it wasn't something as complex as, birthdays out of the year. Let's say if somebody, like if Ever went up to 10 different people and said, here, flip this coin. And let's see where it winds up. Okay? So if 10 people flip the coin, and then she was looking at the probability of it landing on heads. Okay? So the 10 would go down here at the total number of observations in this formula. And let's say if it was, what did I say? 5 tails? If it was tails 5 times out of the 10, then the 5 would go in the top. So relative frequency probability is, in other words, what did happen. Somebody actually collected data. They actually made observations. Sometimes it doesn't always have to involve a coin. Like let's say you're just, observing cars at an intersection, and they've only got 2 options. They can go right or they can go left. And you observed, let's say, 25 cars. All right, so 25 is your total number of observations. And let's say you're only looking at the amount that turned left. So the number that turned left, let's say it was, 13. So that'd be 13 out of 25. That would be your relative frequency probability. Okay? So again, the difference, theoretical probability is what should happen based off what you know about how many outcomes there could be. Relative frequency probability is what did happen. What did you actually see or record or hear, that actually happened. So let's do another example with this one. Let's go to number 29 on page 423 in your textbook. Number 29. Okay. All right. So 29, relative frequency probabilities. Use the relative frequency method to answer the following questions. All right. So let me get set up here. Okay. Relative frequency probability. All right. And remember, this is, in other words, what did happen. All right. So it's not a hypothetical like theoretical was. This one is that someone actually made some notes, took some data, so on. Okay, so 29 says, the local weather forecast has been accurate for 18 of the past 30 days. Based on this fact, what is the relative frequency probability that the forecast for tomorrow will be accurate? Okay. So, the way that we do this one, let's recopy the formula. All right, so the formula for relative frequency probability, P of A, which again means probability of event A, is equal to the number of times that A occurred. I think there's 2 R's in that. Over the total number of observations. Notice how on theoretical probability, the bottom said total number of outcomes. Outcomes meaning, what they should be. Observations is being, what did you see? So, this question says, local weather is right 18 out of 30 days. What's the relative frequency that they're right tomorrow? All right, so substitute in what you know. Again, it's best, even with theoretical probability, it's best to put your outcomes in first. That way you have your total already figured out. Same thing here. It's best to do the total part first, at least for me anyway. So we know that it said the local weather was accurate 18 of 30 days. So 30 there, 18 there. Okay. Unlike 31 over 365, 18 over 30 will reduce. All right, it'll reduce down to 3/5. Or, to make it a little bit easier to understand, this means that there is a 60% probability that tomorrow's weather forecast will be accurate. What does they say about weathermen are the highest paid guessers in the world? That's all a forecast is a, it's like a, hypothesis, educated guess. So, yep. Oh, yeah. Thank you for pointing out my flaws. All right, so does everybody kind of see the differences between relative frequency? It's a good thing that Ever asked that a while ago, because this is what she was actually thinking of. Now, to go back to the birthday question, yeah, we could, do like, say survey 10 people and figure it out. But, to kind of have enough data, we would have to be looking at 10 people that we know had a birthday in January. Or we could just do, 10 random people and then record it and say, all right, what's the probability of birthday in January? So it would be a little bit different. Okay. So anything else that we need to cover right now about relative frequency? We'll come back to these when we start looking at more examples and stuff. But everybody okay for now? All right. There's always a good chance that you guys are better at probability than I am anyway, so there's something that you can lean on. Okay, so the third kind, subjective probability. Now, with this one, you're not really figuring anything out, okay? This one is just kind of like an estimate, or more of a guess than the other two are. So subjective probability is an estimate based on experience or intuition. So it's, in other words, it's what you think will happen. All right? We've all been in that situation where you're out with your friends or your family and you're doing something, or you're like, say if you're watching March Madness right now, and someone needs to hit a game-winning shot, and you say something like, "Oh, there's no chance that he makes this shot," or "There's a 100% chance," or something like that. You're just kind of guessing, in other words. So here are some examples. This one came out of the book. I'm 100% certain you'll like this car. We've heard that, whenever we go to buy a car, because they're trying to sell it to us. This one happened to me, pretty much. I'm 80% sure I just broke my foot. I ran it. My parents had bought a replacement gutter when I was in high school because the other one had fallen off the house. And I was coming home late one night, and the porch light wasn't on, and I kicked the living daylights out of that gutter because it was still laying on the porch. Cut my foot, thought it was broke. Just bad. And then this one, I've said so many times watching my beloved Titans play, especially this past year, there's zero chance they score a touchdown. So it's just something that you kind of say when you're watching something, or you're observing something, or talking about a specific situation, and you're just providing what you think will happen. That's why it's subjective. Subjective is specific to a person. So not really anything to figure out with that one. Okay. The book mentions something called the fairness test on page 416 and 417. All right. So it's kind of at the bottom of 416 and is mainly talking about coins. But what it's getting at is this. Because, we've talked about, the two frequencies that we have to figure out, relative frequency and theoretical. What the fairness test is saying is within a certain experiment, compare them. Okay? Look at the same set of information. Look at, your supposed data and your collected data. If the results are close to the theoretical numbers, it is fair. If it's not fair. Most of the time it's used on things for, gambling, like coins and cards and stuff like that. So let's look at the fairness test. There is a pretty good example in the book on 416 and 417. Okay, so the bottom of page 416, it gives you a situation, and it says, if you're interested only in the number of heads when tossing two coins, then the possible events are 0 heads, 1 head, and 2 heads. That's all 3 of your possible outcomes, right? Suppose you repeat a 2-coin toss 100 times, and your results are as follows. 0 heads occurs 22 times, 1 head occurs 51 times, and 2 heads occurs 27 times. Compare the relative frequency probabilities to the theoretical probabilities. Do you have reason to suspect that the coins are unfair? All right. So where is 7.1? Oh, it's on the back page. No, it's not. Hey, Lord. Okay. So, theoretical probabilities. So the 3 outcomes that we had were 0 heads, 1 head, and 2 heads. Because you're flipping 2 coins each time, right? Okay, now, the theoretical probability. So, how many coins are you flipping? 2. How many sides does each coin have? 2. So, that makes 4 possible outcomes for each situation, right? Okay. So, let's see here. Over on page 411, it shows you that there are, those are the 4 outcomes. So coin 1 and coin 2 both landed on tails. Coin 1 and coin 2, one of them was heads. Coin 1 and coin 2, the other one was heads. And then coin 1 and coin 2, they're both heads. So that means that the theoretical probability of both of them landing on tails is 1 out of 4. All right? Now, as far as them being 1 head, you could have 2 coins, one's head, one's tails, flip again, and then it switches, right? So this is 2 out of 4. or 1/2. All right. Yeah. Okay. And then 2 heads is only one of the outcomes, so it's only 1/4. So as far as percentages, that's a 25% chance of happening. This, where it's, only one of them heads, is a 50%, and then this is also 25%. Okay? Now, this was the theoretical ones. Okay? So in other words, like we said, this is what should have happened. Okay? So now let's look at the relative frequency. Okay? So relative frequency is what did happen. Relative frequency. Okay. So in example 7, it tells us what the observations were. It says that 0 heads occurred 22 times, 1 head occurred 51 times, and then 2 heads occurred 27 times. Okay, so looks like a 6. Can't do anything right today. All right, so 0 heads was 22 out of 100. Well, luckily, as far as percentages, if it's already over 100, we know what that percent is. 22%, right? 1 head occurred, was it 51, did it say? Yeah, occurred 51 times out of 100. So that's easy, 51%. And then 2 heads occurred 27 out of 100 times. So that is 27%. So our theoreticals, 25, 50, 25. Our relative frequency, or the ones, that did happen, 22, 51, 27. So those are pretty close, right? So basically what the fairness test is asking is there any reason to suspect that there was some funny business that went on with the flips or with the coin, of anything like that? And no, 22 is pretty close to 25, 51 is really close to 50, and 27 is really close to 25. So that was a pretty good observation. In other words, it's asking, was there any bias? Was there any kind of outside factor messing with the data? It looks like there was. All right. Okay. It's a good time to take a break. We'll go ahead and pause here for about 10 minutes, and then we'll come back and we'll start talking about how to find out when the chance of an event not occurring. So we'll go ahead and take our break. Okay, let's talk about events not occurring and odds. Right now, let's just talk about events not occurring. If you flip back over to page 412, all right, so on page 412, it talks about how a probability of 0 versus a probability of 1 is comparing something being impossible to it being a 100% certainty that it will definitely happen. All right? For instance, probability of 0. Me sprouting wings and flying out of here. Not going to happen. Right? But if I take a pistol and aim it at my foot and pull the trigger, that is a probability of 1 that I'm going to have a hole in my foot. Right? So, things that are impossible, pigs flying, or something being certain. So here's how they justified it. So throughout the book, it talks about, something being considered likely or unlikely or certain or impossible. So the way they did it was, out of 100. So 0 is impossible, 1 is certain, 1 is acting as 100%. So halfway across, right here, is where they consider an even chance, or 50%, 50-50 shot. If you're gambling, that's called a push. 50% chance they're going to win, 50% chance they're going to lose. All right? So anything from 0% to 50% is considered unlikely because it's got a less than a 0.5% chance or a less than 50% chance of happening. Whereas 50% to 100% is considered likely. Think of your grades for a second. Okay? If you finish this class with what equates out to be a 60%, it's likely you're going to pass. Especially since 60 is the cutoff for passing. Yeah, 10-point scale. So 90 to 100 is A. What is it? 80 to 89 is a B. 70 to 79 is a C. And then 60 to 69 is a D. So anything below 60, no bueno. Or in other words, if we're being polite, it is very unlikely that you will pass. He said with a smile on his face. But I think most everybody in here is in pretty good shape, so I wouldn't worry about it. But yes, so in terms of probability, gambling, estimation, like let's say you're out at the lake with your friends and someone's trying to jump across a creek. And you say, it's very unlikely they're going to make it across the creek. That means that you're going to give them anywhere from a 0 to 50% chance of falling in the water. Subjective probability. Boring. There you go. So, everybody kind of got a grasp on that now? Where those terms come from? So, there actually is a probability of an event not occurring. So we've seen theoretical and relative frequency. As far as setup, meaning they're both being divided, they're pretty similar. But for an event not occurring, which would be considered the probability of event A not occurring, or P of not A, the formula is 1 minus the probability of event A. Now the 1 comes from a couple of places. One we just talked about. 1 is absolute certainty, right? It's considered 100% in other words. So the probability of it not happening is you're going to take 100% and subtract the probability of it happening for sure away from it. All right, so let's see an example. Flip over to page 423 in your textbook. All right. There we go. All right. So 423 in the textbook. And we're looking at number 35. 35 through 38, event not occurring. Determine the probability of the following events. State any assumptions that you use. Well, we're not going to worry about that. Oh, threw the marker in the floor. What else can go wrong today? Okay, so 35 says, what is the probability of not, we'll say, rolling a 2 on a die? I think the question actually said a fair die. So now we know what fair means, right? Even chance of all 6 sides popping up. Okay, so the first thing that you want to do is go ahead and find the probability of the 2 rolling up when you roll it. So we're going to go ahead and find P of A. P of A meaning the probability of a 2. Well, how many sides are on a die? And which one of them has the 2? One of them does. I guess I should say how many of them have a 2. How many of them have a 2? Yeah. So the probability of A is 1/6. Okay? Now, here's another explanation of where that 1 in the formula comes from. The probability of A plus the probability of not A, or, you could also rephrase it as everything else besides A, should add up to a 1. All right? That's how you check it. All right? So in other words, the probability of 2 plus the probability of not 2 should equal 1. Well, if we know that the probability of 2 is 1 out of 6, then what's the probability of not 2? Everything else, which is 5 out of 6. Yeah. So you can do it that way. But to use the formula, we'll do it over here. So the probability of not A, which means the probability of not 2. Okay? So probability of not 2 is equal to, got peas flying all over the place here. So 1 minus the probability of A. Okay? So the probability of A was the probability of a 2 popping up. So that's going to be 1 minus the probability of a 2, which we already found was 1/6, right? And when you think back to adding and subtracting fractions, 1 equates to a 6/6. 6/6 minus 1/6 is 5/6. All right? So a 5 out of 6 probability of not 2. That wasn't so bad, was it? The hard ones are the ones with cards. Because cards have 4 different suits, right? 52 cards in the deck. 52 divided by 4 is 13. So, you got all different kinds of awfulness that can pop up with a deck of cards. So, on Wednesday, we'll try to look at some more examples with that, because there'll probably be some on your lab whenever I get it built. I don't know for sure. I've got to redo it. All right, so any questions of how to find the event of something not happening? Again, these can get really, really bad. So I'm trying to keep them simple for me and you. Yes, I'm putting myself first because, as I told you, I don't like probability and I'm not good at it. So I'm trying to keep it simple. All right. So let's go to odds, and that should finish us out for today. Okay. We've all heard the phrase, the odds for this or the odds against this, whether it's like a political race or someone trying to make a field goal or a free throw or a soccer goal, whatever it might be. Odds for and odds against. Okay? So the formulas for these two are really just reversed. Okay? So the formula for finding the odds for something happening is the probability of what you're looking for happening divided by the probability of everything else happening. So P of A divided by P of not A. All right? So odds against is the opposite. Everything else divided by what you're looking for. So here's an example. Let's go back to what we just talked about with rolling a 2 on a die. Okay? So the odds for not rolling a 2, which sounds weird to say. So the odds for not getting a 2. So that means that we take the P of A. I'm about to write on this TV screen with a Expo marker. IT would have a fit. So the probability of A from our previous problem goes right here. That's our 1/6. Probability of not A is what we found with our event not occurring problem, which is 5/6. So we're dividing fractions. So just think back to, your basic math. You're dividing fractions. So what that means is that you have to first write them properly, because when you have two fractions inside a fraction setup, it just looks bad, and it's kind of hard to figure out where everything went. So take them out of that and use the division sign. 1/6 divided by 5/6, right? Everybody remember the rule for dividing fractions? There used to be a little saying, dividing fractions is easy as pie. You flip the second one and multiply. Well, I can tell from the pure delight on your face. Most people also refer to it as keep, change, change. Keep the first one, change division to multiplying, change the second fraction to what's called its reciprocal, or in other words, what it looks like when it's upside down. Okay? Yep, keep, change, flip. That works too. Keep, change, flip. That works too. So keep the 1/6 as it is. Change your dividing to multiplying, and change the 5/6 to 6/5. What that does is allows you to go into your cross-canceling or cross-reducing stage. In this case, we've got two 6s diagonal to each other. There they go. So that becomes 1/5 or 20%. So the odds for rolling a 2, the odds for not rolling a 2 is 20%. So the odds of not rolling a 2 versus the probability of not rolling a 2, different, aren't they? They're a little different. All right? Because what odds are, that was really bad grammar on my part. What odds are a comparison. You're comparing the probability of not rolling a 2 against the probability of rolling everything else. Right? So that's the odds for not rolling a 2. The odds against not rolling a 2, you do the same thing you just did, but you reverse the order. So this time, instead of 1/6 divided by 5/6, it's 5/6 divided by 1/6. But everything else is still the same. Keep, change, change. Keep, change, flip, whatever you want to call it. The 6's go away. You got 5/1 or 500% if you multiply that by 100. So the odds against not rolling a 2, which is a sort of a double negative. The odds against not rolling a 2 is kind of the same as the odds for rolling everything but a 2. So, much greater chance of that happening. So in other words, odds for and odds against are reciprocals. They're opposites. Okay? Because if you look at their formulas, they're reversed, right? Okay. A lot of kind of confusing stuff that I threw at you today. And I went through it pretty quick because we had a lot of it to get to, because it's, right now 9:24. So on Wednesday, when we come back in, we're going to kind of brush back over all this stuff again. I'll have your labs ready. We'll take a look at those. All right. Probably not going to be a lot of questions on it. So, as a trade-off, if there's not a lot of questions, they count more. All right. So you got to be careful. But yeah, probability is just a booger. So, all right. Enjoy the rest of your day. We'll see you back on Wednesday. Oh, let me see. Let me see. Let me look. Yes. So, yeah, real quick. Thank you, Kaya and Haley. Yes. You did not have any homework over the weekend because I had to redo the statistics labs. The statistics labs are now available. So you've got both parts there to do. So yes, they opened today and they are due the 27th. Thank you for reminding me about that. But no, you did not have anything that is due like today or tomorrow. You didn't have anything over the weekend. No, because I The labs that I'd made back in the fall, got to looking at them, and I was like, nah, that's not what I want to do. So I trashed them and I redid them. Doing the same thing for probability. I was looking at them and I was like, nope. So let's do something else. Okay. You too.